Hello, I'm Raphael Hauser from the Oxford Mathematical Institute, and I'm presenting joint work with Armin Eftekhari from the Turing Institute and Henry Matzinger from Georgia Tech. This is a promotional video of the talk we will give at KDD 2018. PCA is a dimensionality reduction tool for high-dimensional datasets. It offers a solution to the problem of finding a low-dimensional linear subspace with the property that when the data vectors are projected into this subspace, they don't change their distribution much. Pairwise distances between the data points, the dispersion of the data, and data clusters should all be preserved as well as possible. This can reduce overfitting issues in machine learning and can be seen as a more abstract representation of the information carried by the data. More formally, say A is an m by n data matrix with rows that correspond to samples and columns to features. We project this data onto the column span of a matrix X with orthonormal columns. The projected data matrix AX still has m samples, but now only r features, thus reducing the dimension from n to r. PCA chooses X by solving the displayed optimization problem. The problem can also be reformulated in terms of the trace operator applied to the sample covariance of the projected data. We call this the trace program. We now take a different approach to linear dimensionality reduction by replacing the trace by the determinant. This model, which we call the determinant program, is known in theory to yield the same solution as the trace program. This is never exploited algorithmically, but worth revisiting because the determinant program has the key advantage of being invariant under arbitrary basis changes, while the trace program is only invariant under orthogonal basis changes. We may thus enlarge the feasible set of the determinant program to the set of n by r full rank matrices, thus rendering the optimization model effectively unconstrained. While the trace and determinant programs yield the same solution in standard PCA, the results start to differ when additional structures imposed on X, such as sparsity, a feature that is associated with ease of interpretation. Since orthogonality and sparsity are somewhat competing requirements on X, the less constrained determinant program now has a crucial advantage in finding a good solution. To turn this into a practical tool, we need to use an optimization algorithm to solve the determinant program. As the optimization model is non-concave, we may worry that the algorithm gets stuck in a local rather than a global maximum. Luckily, we can show that this cannot happen. In our talk, we will prove that all stationary points that are not global optimizers are saddle points. This insight is important because line search ascent algorithms cannot get stuck in saddle points and will always find the global maximizer. We will also present numerical experiments that show that the determinant program is more stable than the trace program, resulting in faster convergence rates and clock times. Thank you.